So I know that you're familiar with most of the concepts of cellular aging, but I thought that it was a good idea to put together a lecture that summarizes all of the different components of cellular aging. So let's begin by looking at how we define aging. Is aging growing up? Is aging growing old? And then what is really old anyway? And how do we actually define aging? And as it turns out, there isn't really a solid definition of how we define aging, but I'm pretty sure we all have a good concept of what aging looks like. So let's think about the idea that it's an intrinsic process where we have interactions with environment, which could be things like sunlight and toxins and the things that we consume in our diets that cause changes in structure and function of our cells and all of the molecules within them. So if you could think for a moment about all of the things that you know that could contribute to cellular aging, what sort of things would you come up with? Well, we can categorize all of these things, these physiological traits of aging, into 9 different categories. We start out with genomic instability, and I'm sure that already you could put a number of things in that category. My intention in this lecture is to put all of those things in those categories or in these categories for you so that you have it all together and are well prepared on the topic of aging for your exams. So in addition to genomic instability, we have mitochondrial dysfunction and telomere attrition. All of these should be pretty familiar topics, right? We have epigenetic alterations, loss of proteostasis, altered intercellular communications, cellular senescence, as well as deregulated nutrient sensing and stem cell exhaustion. So these are 9 categories of things that can or that do change as cells age and lend themselves to some of the phenotypic manifestations of aging. So we will move through these categories fairly rapidly as I summarize some of the things you already know quite a lot of details about. When we consider genomic instability, we are going to consider that we accumulate genetic damage throughout our lifetimes. So in the form of DNA lesions, through mutations, through environmental interactions and such. So we have both nuclear DNA and we have mitochondrial DNA to consider in this realm of accumulating genomic damage and thus instability of genes and perhaps interruptions or changes in how genes are transcribed and translated. Also, we need to consider the nuclear architecture, so all of the components that go into the nucleus and keeping that system of DNA transcription working efficiently. So when we consider genomic instability, we have both exogenous threats, things that impact it from the outside, as well as endogenous threats. Outside influences can be physical influences or chemical influences in the form of things we are exposed to during life, as well as biological influences from within ourselves and outside of ourselves. So in our endogenous threats, we really are now considering replication errors, spontaneous hydrolytic reactions, as well as damage that can be done by reactive oxygen species. So all of our metabolic processes, cell respiration, the final electron acceptor is oxygen, right? And you are familiar with the idea that oxygen, when we split the O2 into 1/2 of an O2, it is highly electronegative and can run around and do all sorts of damage to our DNA. And as it happens, it's kind of paradoxical. We require oxygen to live, but oxygen in the end is potentially what actually leads to aging and eventually death. So something to roll around a little bit there.